Hi, I'm Robert Rojas. In this video, I will demonstrate how the Markov chain works. Some important underlying concepts will also be discussed so that it will be easy to appreciate the beauty and importance of the model. Let's start now. Let's start from the very foundation of Markov chain. Let's understand the idea behind Markov assumption. Markov assumption is the assumption that the probability of a word depends only on the previous word. This means to say, we don't have to bother about the probabilities of the previous words except the word just before the current word of interest. This will be illustrated in a while. Now let's talk about Markov models. Markov models are the class of probabilistic models that assume that we can predict the probability of some future unit without looking too far into the past. In other words, a Markov model embodies the Markov assumption on the probabilities of this sequence, that when predicting the future, the past doesn't matter, only the present. Let me interpret the formula that is shown in the screen. The formula states that the probability of a word q sub I, given a sequence of words from q sub 1 to q sub I minus 1, is just the probability of the word q sub I, that is the current word, given the word q sub I minus 1, that is the preceding word. Now let us discuss the Markov chain. Markov chain is a stochastic model describing a sequence of possible events in which the probability of each event depends only on the state attained in the previous event. A Markov chain can be thought of as a finite state automaton as shown in the screen, where its arc is associated with a probability indicating how likely that the path is to be taken. A Markov chain makes a very strong assumption that if we want to predict the future in the sequence, all that matters is the current state. All the states before the current state have no impact on the future except via the current state. Markov chain is useful when we need to compute a probability for a sequence of observable events. It contains the following components. 1. The set of end states of the transition graph or finite state automaton. 2. A transition probability matrix where its a sub ij represents the probability of moving from state I to state j, such that the sum of all probabilities leaving state I is equal to 1. 3. The initial probability distribution, where its pi sub I is the probability that the Markov chain will start in state I. Some states j may have p sub j equal to 0, meaning that they cannot be the initial states. Again, the sum of all probabilities leaving state I is equal to 1. 4. The initial state of the transition graph or finite state automaton, which is a special start state not associated with observations. 5. The final state of the transition graph or finite state automaton, which is a special end or final state not associated with observations. Suppose we have a transition graph as shown on the screen. It has 5 states, namely the start marker, stone, R, hard, and end marker. 2 of which are the starting state, Q sub 0, that is the start marker, and the final state, Q sub F, the end marker, respectively. The pi is equal to 0.48, 0.17, and 0.35. The transition probability matrix is generated as follows. For the word stones, the different probabilities as shown in the arcs leaving the state labeled stones are pointed to by color-coded arrows, and they are reflected in the second row of the transition probability matrix. For the word R, the different probabilities as shown in the arcs leaving the state labeled R are also pointed to by color-coded arrows, and they are reflected in the third row of the transition probability matrix. For the word hard, the different probabilities as shown in the arcs leaving the state labeled hard are also pointed to by color-coded arrows, and they are reflected in the fourth row of the transition probability matrix. Of course, the end marker does not have any path leaving such a state, so the fifth row of the transition probability matrix contains 0 values. For example, what is the probability of the sentence "stones are hard" appearing in the language? Let's demonstrate it by having some example computations that will be shown on the screen. The probability of the start marker, stones are hard end marker, is equal to the probability of stones given the start marker times the probability of R given the start marker stones times the probability of hard given start marker stones R times the probability of end marker given start marker stones are hard. The formula gets complicated as the sequence gets longer, but it can be easily solved by applying the Markov assumption, which I will show in the screen. The probability of the start marker, stones are hard in marker, is equal to the probability of stones given the start marker times the probability of R given stones times the probability of hard given R times the probability of end marker given hard. So that will just be the probability of stones given the start marker, which is 0.48, times the probability of R given stones, which is 0.36, times the probability of hard given R, which is 0.048, times the probability of end marker given hard, which is 0.28. So the probability of the start marker, stones are hard end marker, is equal to 0.02322. Another example, what is the probability of the sentence "Are stones hard" appearing in language? The probability of the start marker "Are stones hard" end marker is just the probability of R given start times the probability of stones given start marker R times the probability of hard given start marker R stones times the probability of end marker given start marker R stones hard. Applying the Markov assumption, the equation becomes the probability of start marker R stones hard in marker equals the probability of R given start marker times the probability of stones given R times the probability of hard given stones times the probability of end marker given hard. So that will just be the probability of R given start marker, which is 0.17, times the probability of stones given R, which is 0.32, times the probability of hard given stones, which is 0.15, times the probability of end marker given hard, which is 0.28. So the probability of start marker R stones hard in marker is equal to 0.00228. So the probability of stones are hard is equal to 0.02322, and the probability of R stones hard is equal to 0.00228. This means to say that the sentence stones are hard is more likely to appear in the language than the sentence are stones hard. Of course, the sentence are stones hard can appear in the language, especially in the interrogative statements. Thank you very much. I hope these lecture notes in audiovisual form have helped you in some way in understanding the concept of Markov chains in your computer science journey. Bye!